Oh, hi mechanics friends. I don't know if you've heard, but Megastrain is onto us. He knows where we're at. He's out to get us. He's after the all-stress cube. We're gonna need to hurry if we're gonna outsmart him, if we're gonna defeat him for once and for all. A couple things we're gonna need to do along the way though. I think we're going to need to define plane stress, derive the stress transformation equations using equilibrium, explain principal stresses, develop equations for principal stress and max shear stress, and then use stress transformation to solve some engineering problems. I hope you guys are up to the task. In this lesson, we need to talk about stress transformation. It's of dire importance to the whole human race. I hope that you won't just be an Autobot, not paying attention. I promise I will not Decepticon you. But we need to get to the bottom of stress transformation. And so to do that, I need you to start by drawing an arbitrary object.
To get started on stress transformation, I would just want you to take a look at this arbitrary object with some random forces on it, random support conditions. We want to be able to identify the stress distribution on a single element within this body. So it doesn't matter what's happening. We want to be able to sketch this element with all of the appropriate stresses acting on it.
I have here the all stress cube. This is going to help us with stress transformations. Now the goal of stress transformation is to figure out at any point in an arbitrary object with any kind of loads on it, what's happening at one isolated point. So whether we're designing a car, a frame, a mechanical part, or a building, whatever the case might be, we always want to come in and identify one point of interest. And so we represent that using this six-sided cube. So if you go ahead with your random object, what I want to do is I want to pull that cube out of the object. And we want to examine what is happening on this cube. So we talked about a few different types of stresses in this class. We've talked first about normal stress. So we said normal stress was when we had a stress pulling or pushing on an object. Normal stress is defined as normal because it's normal to the plane on which it acts. So if we go back to calculus and vectors, we talk about a vector, we can describe the plane that that vector acts on by the normal to the plane. So this is normal stress, and we would call this maybe normal stress in the x direction, normal stress in the y direction, and of course we could have normal stress in the z direction. In addition to normal stress, we talked about shear stress. So shear stress is defined as a stress that's in the plane in which it acts. So in this case, the stress would be in the plane of the cube. So this stress, this shear stress, is what we would call tau xy. It's called tau xy because it's acting on the x plane. So if this is our x-axis, this is the x-plane. So it's acting in the x-plane in the positive y direction. So this is tau xy. We could also have tau xz, and that would be in the x-plane coming out of the page. So we see that on each surface, we have a normal stress, and then we have two shear stresses. And those three stresses are orthogonal to each other, and that's the max that we can have in a three-dimensional Cartesian coordinate system. We can have those stresses in the on the x-plane, on the y-plane, and the z-plane. So that gives us a total of 9 different stresses acting at a particular point. So this is the end goal. We want to know what stresses are acting on this, what normal stresses, what shear stresses are acting at a point. And then what we're going to talk about in a couple lessons is determining failure. So it's not just good enough that we can describe the state of stress on this block, but we will want to know whether or not this is going to fail. If our stress cube fails us, I think you know that Megastrain will have won. Alright, so let's go ahead and sketch those stresses in our notes.
Back in our notes, let's add the stresses that we just talked about. So we have the normal stress, this is sigma x. Sometimes people call this sigma xx as well, so you might see that notation in engineering mechanics. Sigma x is the normal stress to the x-plane. The reason for the second x would be it's the normal stress to the x-plane in the positive x direction. So we'll see that nomenclature when we talk about tau. So tau xy is our shear stress, and it is the shear stress on the positive x-plane in the positive y direction. So the subscript xy means it's on the positive x-plane in the positive y direction. So remember from mathematics that we can always define a plane by its normal vector. So the plane on the right side of this cube has a normal vector in the positive x direction. So this is the positive x plane, positive y direction. I just drew in here a shear stress that was on the positive x plane in the positive z direction. Now we can go to the other two sides of the cube. We have the positive y plane, which is on the top of the cube. So we have the normal stress, sigma y, in the positive y plane. And then we have the two shear stresses, tau yx and tau yz. Finally, we can go to the third plane, the positive z plane. We have sigma z, and then we have tau zy and tau zx. I've drawn all of these stresses, the normal stresses and the shear stress, in our positive sign convention. So the positive sign convention, again, is positive x plane, positive y direction, for tau xy, for example. Or tau yx, positive y plane, positive x direction. So if you have something that's in the positive x plane but in the negative y direction, that would be a negative shear stress. Or if you had something on the negative x plane in the positive y direction, then that would be also a negative shear stress. I haven't sketched it on here, but we would have equal and opposite forces on the other planes. So I kind of pointed to them here. So the left edge of the cube would be the negative x plane. The negative y plane would be located on the bottom of the cube, and the negative z plane on the back side of the cube. So that gives you an idea on the sign convention that we'll use. This is all positive stresses, and also the nomenclature. Remember, sigma is normal stresses and tau represents shear stresses. Counting up the variables, we see that we have 9 stress components to define the state of stress at a point. In fact, if you go on to advanced mechanics and materials, you might even refer to the stress matrix. It would be a 3x3 matrix representing the stress components at this point. However, we will see from equilibrium that tau xy has to equal tau yx, and likewise tau xz equals tau zx, and tau yz equals tau zy. And so taking this into account, we can then state that we have 6 unique components to define the state of stress at a point. So in 3 dimensions, we need 6 components of stress. That's 3 normal stresses and 3 shear stresses to fully define the state of stress at this particular point.
Alright, so I hope you can see the value of this cube and how it represents the states of stress at a point. I'm going to need you guys to protect this for the rest of the year. We're going to deal a lot with this cube for the rest of our course, so I need you to safeguard it and keep it away from Megastrain. I hear some noises. He might be close. Better keep this under wraps.